Good morning, students. The last class we were talking about the torsion of circular bars using Prandtl method. Okay. Now we'll see the same. The torsion of elliptical bars using Prandtl method. Okay. Now, so what we have done in case of circular cross section, the same step we have to repeat. Okay, first of all we found an general expression for circle, that means x square plus y square is equal to c square. Similarly, the general expression for elliptical bars is x square by a square plus y square by b square is equal to 1. And then now find out a value for this. You take this one and multiply it with m. So that is our Prandtl stress function. In circular, the Prandtl stress function was m into x square plus y square minus c square, right? Here it is m into x square by a square plus y square by b square minus 1. Okay, the same pattern you need to follow. Okay, and you know that del square phi is equal to minus 2g theta. So the next step that we have done in case of Prandtl function for circular cross section is find out whether this condition, okay, this condition you need to prove. Not proving, you need to get this to this step. Okay, so del square phi, you differentiate it twice, you'll get 2m by a square, and here this is 2m by b square, right? And so del square phi is nothing but 2m into 1 by a square plus b square, and from that you find out the value of m. Now in circular as well as in this case, you just substitute this value in this equation. Okay, now you will get the value of phi, and now onwards you need to differentiate this value of phi. Okay, so now you will find the shear stresses and its resultant shear stress. Shear stress is dou phi by dou y, and dou yz is minus dou phi by dou x. You just differentiate it. You have put the value here. Here constants are, these terms are constants only with y. So 2y will be here, 2y by b square, right? Okay, that will remain here, and in the here 2x by a square will be coming. Okay, right? Here you will be having 2x by a square. So this is the value of tau zx, and this will be the value of tau yz. And you square and under a root, then you will get the resultant shear stress. This is same method that we have adopted for circular cross sections. So you got tau as resultant shear stress as this value. Okay, now after that you just go for finding torque, the same equations we had here. Okay, so 2 into double integral of phi value, you substitute the phi value from here and differentiate it with respect to dx dy. So just substitute it, phi value, that's all, and you'll see you need to differentiate x square y square with respect to dx dy. So I will separate it here. This is a common term which is taken outside. Okay, and here I'll be taking 1 by a square, x square into dx dy, x square dx dy. 1 by a square is taken outside because it's a constant, and here I am splitting this, that's all. Y square by b square means 1 by b square double integral y square dx dy, and minus 1 dx dy. Okay, so dx dy is nothing but dA, right? So x square dA is nothing but moment of inertia with respect to y axis, and y square dA is nothing but moment of inertia with respect to x axis. And double integral dA, or sorry, single integral integral dA is nothing but a of what? Ellipse, that is pi ab. Okay, see, ix is y square dA. Okay, I by is x square dA, and this integral dA becomes if you integrate dA, it becomes area of ellipse is pi AB, right? Okay, you substitute all these values, minus 2g theta a square b square by a square plus b square iy by ixx pi AB. You just do that. Okay, now the inertia with respect to x-axis for an ellipse is pi AB cube by 4. This you need to mug up. Okay, if you don't remember this from your basic mechanics, you just note that ixx and iyy of an ellipse. Okay, substitute these values here. Okay, then you will get a common term of pi AB. In all these things you will be having pi AB as common. Okay, do the LCM works, and at last you will get torque value as pi a cube b cube by a square plus b square into g theta. Okay, so from here g theta is this value, and if they can ask in terms of theta as well as in terms of torque. Okay, that's all. Okay, so this is very important thing. Okay, now what I am going to do is that g theta, you have a g theta here, right? In the first equation of phi, g theta you have a value for g theta here also. Substitute this g theta in that equation. Okay, then just substituting, what happens? 6 in 5. I have already mentioned the terms where and where you need to substitute. You just do that, that's all. Okay, phi will be minus t by pi AB into x square by a square plus y square by b square minus 1. Now you got the value of phi here. Tau zx is dou phi by dou y. You differentiate this value. Okay, you will get tau zx is minus 2t by pi AB cube, and tau zy will be 2tx by pi a cube b. Total shear will be 2t by pi a cube b cube, a power 4 y square plus b power 4 x square raised to 1 by 2, and tau max is 2t by pi ab square. Okay, so these same results we attained it for elliptical cross section when we do problems regarding or problems in Senman's method. Okay, fine. So go through these equations that which are highlighted are very important. We need to do problems regarding that. Okay, so in the next lecture we will be doing some problems regarding elliptical and circular cross sections, and I will also just briefly explain how these derivations of Senman's as well as Prandtl has come. Okay, thank you.